Welcome back to the Math Professors. If you're looking for content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover outward flux using the Divergence Theorem. So the outward flux is the triple integral over d of the gradient dot f dv. Now, the gradient dot f is this dot product between the gradients and then your vector field, m, n, and p. And when you do this dot product, you can see it's the partial with respect to x of m plus the partial with respect to y of n plus the partial with respect to z of p. So what I want to do is I want to determine the outward flux on a thick sphere bounded between 1 and 2. So given this vector field of the square root of x squared plus y squared plus z squared multiplied by xi, yj, zk. Now I wrote it in this term as well because I was using them over here. Okay, so in order to do this, we have to start by finding the divergence. So we're going to need the gradient dot f, which is going to be the derivative with respect to x of, well, our m, which is going to be the multiplication of these two things. So this is going to be, x times the square root of x squared plus y squared plus z squared. And then plus the derivative with respect to y of, well, it's the same thing. It's this times y now. So this is going to be y times the square root of x squared, y squared plus z squared. And then finally plus the derivative with respect to z of, very similar, z times the square root of x squared plus y squared plus z squared. Now it looks intimidating, but once we do the first one, the other ones are done very similarly, so I'm not actually going to do them by hand. We'll just say pattern clearly. So when I take this thing's derivative, derivative of the first, which is 1, times the second, plus the first, times the derivative of the second, pulling out that power, so 1/2 times x squared plus y squared plus z squared to the minus 1/2, multiplied by the derivative of what's inside with respect to x, which is going to be 2x. Now, let's see, the 2's are going to go away. So we're going to have the square root of x squared plus y squared plus z squared plus x times x is going to be x squared, and then the bottom I'm going to have, or the denominator, we're going to have that square root of x squared plus y squared plus z squared. Now, I'm going to combine like terms, so what I'm going to do is I'm going to multiply, top and bottom of this by, x squared plus y squared plus z squared, and same thing down here. So what we're going to get is x squared plus y squared plus z squared plus x squared all over that radical. And what we can see is that x squared plus x squared is going to give us 2x squared. Now similarly, what we're going to get for this is going to be the same thing, but instead of 2x squared, we're going to have a 2y squared. That'll be for this. And then similar, for this one, we're going to have an x squared plus 2y squared plus a z squared. And similar for the other one, it's going to be, this will be doubled, the other ones will remain the same. So this will be x squared plus y squared plus 2z squared all over that square root of. Now, adding these things together, what I'm going to have is I'm going to have 2x squared plus x squared is going to be 4x squared. I'm also going to have a 4y squared. I'm also going to have a 4z squared. So what I could do is I could factor out that 4, and I'll have x squared plus y squared plus z squared all over this, x squared plus y squared plus z squared to the 1/2 power. And then, when you divide those things, subtract the powers, 1 minus 1/2 is going to give us 1/2, which is going to give us 4 times the square root of x squared plus y squared plus z squared, which, for something that looks so complicated, actually spit out something, relatively nice. Now, let's go back to the bounds here. Now, we're talking about this being done on a thick sphere, because remember, we're going to have to integrate over these bounds. I know the integrand now, it's right here. So since this is a sphere, I would highly recommend against using rectangular coordinate systems. I would clearly use spherical coordinate systems. And so let's rewrite this in terms of rho. Well, x squared plus y squared plus z squared is rho squared. So this is 1 less than or equal to rho squared, which is less than or equal to 2. Or if I want to know the bounds on rho, I'm going to have to square root all these things. So now remember, when we're doing this over a sphere, when you're doing this over a sphere, let me just kind of map out the sphere just to be sure. What we're going to have to do is we're going to first have to integrate rho, which is going to be, the azimuth. So it's going to go from, we're going to integrate it from here to here. So I'm going to start down here, and I'm going to integrate all the way up to here. And then I'm going to spin this thing fully around, and when you spin this arc around, what it'll do is it'll generate this, this whole sphere eventually, as you generated the entire thing around. And then we have to go, remember, it's a thick sphere, we're going to have to go from not 1 to 2, but the square root of 1 to the square root of 2. So that's going to be our bounds. So let's erase this and make this nicer. So what I can do is, so our bounds, we're going to have root 1, which is 1 less than or equal to rho, which is less than or equal to root 2. Now our angle phi, which we went from I go from 0 to pi. Well, I guess it doesn't really matter. I could minus, yeah, 0 to pi is fine. Just need half the circle. And then the other one, we're going to go from 0 to 2 pi. Theta less than or equal to 2 pi. Okay, so this will fully generate that sphere for us. So now now we have the bounds for this. It's going to be the integral from 0 to 2 pi of the integral from 0 to pi of the integral from root 1, which is 1 to root 2 of remember, our integrand is going to be this. Now, turning this into spherical coordinates, we know that x squared plus y squared plus z squared is rho squared. So this is going to be equal to 4 rho squared under the radical, which is going to be equal to 4 rho. So this is going to be 4 rho. Now, remember also when you turn this into your spherical coordinate systems, just like when you turn something from a rectangular into polar coordinates, you get an r dr d theta, but when you do this in spherical, you actually get this is going to be rho squared sine phi d rho d phi d theta. Okay, so integrating this is now going to be 4 rho cubed, so let's write that. So I don't have much room here. And when I integrate this with respect to phi first, what it's just going to do is it's just going to multiply everything, this thing times phi from, actually, we're going to do the rows first. So this is going to be 4 rho cubed over 4, so this is going to be equal to the integral from 0 to 2 pi, integral from 0 to pi of just rho to the 4th sine phi evaluated from 1 to root 2 d phi d theta. So integral from 0 to 2 pi, integral from 0 to pi. Plugging in the root 2 is going to give us 4, yep, minus 1, which is going to give us 3 sine phi d phi, oh my gosh, so close, d theta, made it. Okay, and then now I have to integrate that sine function, so this is going to be the integral from 0 to 2 pi of minus 3 cosine phi evaluated from 0 to pi d theta. So integral from 0 to 2 pi of minus, well, I guess I'll just leave that 3 in there. I should pull the thing out, but it's too late for me now. So cosine of pi minus a minus 3 cosine of 0, the theta, which is going to give us 6. This is -1, and this is going to be +1. So 3 plus 3, which is going to be equal to 6. So this is the integral from 0 to 2 pi of 6 d theta, which is going to be 6 theta evaluated from 0 to 2 pi. Plugging that in is going to give us 12 pi. Boom. If you like the content, please consider liking, subscribing, and sharing. Thank you.